time has come for our last lesson of the year. This is it. We've done everything. Let's get to it before I get all emotional. All right, we're going to find the area and arc length of polar regions. Okay. How do you find the area of a polar region? So you have to remember something. Now, does this formula seem familiar? That if we have an arc or part of a circle, and we know that this angle here is theta, that the area of that arc is given by the formula 1/2 theta times r squared, with the assumption that theta had to be in radians. So that would give you the area of any sector. Now, a polar region, of course, is the same idea. We've got ourselves kind of a sector, but the idea with polars is that this isn't necessarily a continually smooth curve. It could be something like that. How do we find the area of that? Well, it's calculus. You understand. Our goal is to find little pieces that are more accurate and add them all up. And we'll do one more just for fun. Alright, so I have all those little sectors now. And of course that sector is still not quite perfect, but it's closer. And of course the more sectors you have, the closer your answer. And how many do you want? An infinite amount. And then when you do that infinite amount of sectors, you add them up. Alright, so you know the drill, because it's calculus. So what we're going to do is we're going to call each of these changes of the vectors delta theta, the change in the angle. And how long is the distance from here to any point? Well, it's the r value of the function. So the area of a sector would be, we want to add up a whole bunch of sectors. Okay? So we have this formula, so we have 1/2. Now the theta in this case is going to be given by d theta, or delta theta, I'm sorry. And the r, the radius in this case, will still be the r value of this function. So r doesn't necessarily stand for the radius, it stands for the r value of the polar coordinate. Alright, it's calculus. This is, we add a bunch up. How many do we want to add up? That's right, you know it. We want an infinite amount of those sectors. And how do we express that? We express it as the integral, 1/2 is a constant, we can put it outside, of r squared. Delta theta would be d theta. Going from where to where? Well, we're dealing with angles here, so we're going to deal with the first angle, so we'll call it alpha, and the second angle that we'll call beta. So that is your formula for area of a polar region. Alright, so let's use that and figure out the area of this rose curve. Now, I didn't really go over rose curves much in last lesson, so let me show you a little bit about what they are. Alrighty, so here is a graph, r equals sine of a theta. A is a value I'm going to change so you can see what happens to this graph. When a is 1, it's just a circle. Think of it as one petal of a flower where it goes out to 1 and comes back to 0. When a is 2, oh, now we've got 4 petals. It goes out to 1 again, and it comes back to 0. And it does that, goes out to 1, comes back to 0. Goes out to 1, comes back to 0. So there are 4 times between 0 and 2 pi that the sine of 2 theta would equal 0. It would equal 0 at 0. It would equal 0 at pi over 2. It would equal 0 at pi. It would equal 0 at 3 pi over 2, and equal 0 at 2 pi. So it's all about its travel. And when you have 3, notice when you have an odd number, it's the same, the petals are the same as a value. When it's an even number, you have double the petals. Alright, now how do we find the area of one petal of this rose curve? So remember from kind of what we saw, is one petal of this. So we know the petal is going to have a shape something like this. The question is, where does it begin and how long does it take to get back to the origin, or what angle would make that go back to the origin? So what I want to know is, where does 2 sine of 4 theta equal 0? So sine equals 0 at 0, at pi, at 2 pi, at 3 pi. So I want to figure out those are both angles that make sine equal to 0. So 4 theta would equal 0. So in this case, theta would equal 0, and theta would equal pi over 4. So this goes from 0 out to here, and by pi over 4 it comes back. And if you actually look at the graph, and it's not drawn perfectly well, but pi over 4 is the angle that kind of encloses that petal. All right, with that in mind, because that's probably the trickiest part to do about these arc lengths, about these areas, is finding the actual angles. But it starts at 0 and goes to pi over 4. And you can put this on a graphing utility if you want, if that helps you out. Any way you can get to figure out where it starts and how it gets back to 0. All right. I am sure that you can take this and do this by hand. I am no doubt that you will. I don't want to. We have to use a double angle formula. We have to do all kinds of stuff. I just do it in a calculator. This is the answer I got, which I know equals pi over 8. Now, I didn't get pi over 8 by doing anything magical. I did it because I recognized pi over 8 was 0.785. So that's the area of a rose petal of that curve. Now, what if we had 2 polar regions and we want to see where they intersect? All right, so we got to graph these. Oops, let me try straight lines. That might help. All right. So what we got here is we have a graph. We're going to say sine of 2 theta. Now, because it's 2 theta, that means it's going to be a petal. How long does it take for that petal to come back? Well, 2 theta, or it's a sine of 2 theta, I'm sorry. Where does that equal 0? That equals 0 when 2 theta will equal 0, or when 2 theta will equal pi. So in this case, 0 is where we start, pi over 2 is where it comes back. So it comes out, and it comes back at pi over 2. Now the rest of the graph follows the same, oops, that's not a good graph. See if I can redo that part. The rest of the graph comes back and follows the same shape. So it looks something like this. Not a great graph, and that's really poorly drawn. And our cosine of theta is actually a circle that comes out this way. Whoa, it's got to be a circle. All right, so you're going to see we have 2 intersections here and here. So how do we find the area of those? Okay, the first thing we have to find out is, where do the things actually intersect? And would you agree that this graph is, well, should be symmetrical, and therefore these 2 areas are congruent to each other, equal to each other? I think so. In fact, here's what I'd like to do. I'd like to actually use this. I already had graphed it. The red graph is 2 sine of theta, and the blue graph is cosine of theta. And here are our 2 intersection points. We're looking for the area of these. All right, this looks much more symmetrical when it should be drawn correctly. So we're going to find just the first one. So what we have to do, what we really have to find, is this point. So I have drawn a line from the origin that breaks that graph up into 2 parts. All right. So I'm going to find the area of that, but I haven't yet found out this point. That's what I got to find out. So let's find out where these 2 points meet. I'm pretty sure we can see that it meets here at 0, 0. What I want to know is where does the sine of 2 theta equal the cosine of theta? Now, I don't know how much you remember from trig identities and whatnot, and we're certainly not going to harp on those right now. But the sine of 2 theta is 2 sine cosine. And remember, all of these are listed in your textbook and are available online. I don't know how many if you'll need. I mean, you might need this one, but they're available. Or if you want to find the intersection point, you can do it on a graphing utility. Go ahead and do that too. Okay, so let's subtract cosine from both sides. All right, it should be a cosine. And that should equal 0. We'll factor out a cosine. Leaves us with 2 sine of theta minus 1. So here I got 2 possibilities. Cosine of theta equals 0. And 2 sine of theta minus 1 equals 0. All right. Theta, cosine would equal 0 at pi over 2. And if I solve this, I get sine of theta equals add 1 divided by 2, 1/2. Where is the sine equal to 1/2? Well, the sine is equal to 1/2 at pi over 6. So this is pi over 6. And just so you know, the pi over 2 comes from here. If you notice this green part of the graph, you see how it's bounded between pi over 6 and pi over 2. If you really look at it closely, this pi over 2 is tangent here as you get closer to the point 0. So our 3 values are this. So here is 0, there's pi over 6, and here's pi over 2. Alright, so let's make a new page, and let's figure this stuff out. So I'm going to clear this stuff off. Now we're going to go with our formula. So the area of the red section is 1/2. We're going from 0 to pi over 6. And the red section is the sine of 2 theta. Plus, now we're going to add the other section. By the other section, I'm talking now about this up here. Alright, so what's the area of that? So that area starts at pi over 6 and goes to pi over 2. And that graph is cosine of theta. Oops, I forgot to square that. Because remember, it's 1/2 the integral of r squared d theta. Alright, well, now we figure that out. Now I know that we're going to multiply all of this by 2, because when I figure out the area of this, I'm going to have to double to get the area of that. And I just put that in the calculator, and I got 4606. Again, most likely you can do that by hand, but I'm not concerned really about that, and what I'm concerned about is understanding the calculus behind it. Okay. Alright, we have one last problem and one last topic, the arc length of a polar curve. Now this is interesting. I'm not going to take the time to show you because it's lengthy but not difficult. If you remember, we had a parametric equation, just like distance formula. It was the change of x over time squared plus the change of y over time squared. because really it's really Pythagorean theorem or distance formula. Change of x, delta x squared, delta y squared. But we're taking all of them. Okay? There's a way, by using what you know, that x equals r cosine of theta, theta, and y equals r sine of theta. Change that theta, make it look nicer. To turn this into the formula for arc length. Again, I don't actually want to show it to you, just don't have the space. I've included another link to a video where another person explains how this formula gets developed. So if you're interested in seeing how this becomes what I'm about to show you, that is great. Alpha to beta, because remember we're doing angles, r squared plus r prime squared, and we're assuming that that's in terms of theta. So this is the arc length formula for a polar curve. All right, let's use it. So our length will be from 0 to pi, because it's given to, of r squared. So 2 sine of 2 cosine theta squared plus r prime. So why did I do this to myself? Why did I pick a problem like this? I don't know. But let's see. So the derivative of r would be, derivative sine is cosine of this function times the derivative of what's inside, which would be negative 2 sine of theta. Okay, well, we're going to take all of this. Let's move it all over so I have room. So we're going to take this whole thing I just calculated. We're going to square it. I'm going to take the antiderivative of that whole thing with respect to theta. Now, again, I don't want you to bother. I will tell you the answer, though. It is 7.779. Now, you might think, sure, I just looked in the book for that. You might notice it's like number 62 or 64 of the book. I forget which number. And of course, I have all the answers. But I promise you, I put that nasty thing in the calculator and got the right answer. I'm pretty proud of myself for that. But that is all. That is arc length of a polar curve. That is the area between two polar curves and the arc length of a polar curve. That covers every topic that we need to do in Calc BC. So, again, my heartfelt thanks to a wonderful year. I appreciate all your hard work, and I hope you have a great day.